Dynamics is the study of the interactions between objects, and in classical Newtonian mechanics we call interactions forces. And we observe that objects only accelerate when they interact with one another. So an object's velocity only changes when it interacts with some other object. Now, Newton's first law of motion says that an object at rest will remain at rest. We call that state static equilibrium. And an object in motion will remain in motion with a constant velocity. We call that state dynamic equilibrium until it interacts with other objects in a way that produces a non-zero net force. Every force is either a push or a pull, and so it has a vector nature to it, so it's possible for multiple forces to cancel each other out in the way that vectors do. And so an object will be in equilibrium if the net force on it is zero, if all the forces cancel each other out, if they balance, or if there are no forces at all on it. In which case its acceleration will be zero, and we distinguish the two types, static versus dynamic equilibrium, by distinguishing whether the object is at rest and remaining at rest with zero velocity, or moving at a constant non-zero velocity. So that brings us to Newton's second law, which quantifies how much acceleration results from some interactions. So N2L states that at some particular instant, so at one moment in time, the instantaneous acceleration of some object is equal to the instantaneous net force on that object coming from other objects, so other objects exerting the force on this one, divided by the mass of our object. The mass represents the inertia that the object possesses, that resistance to acceleration. And so N2L is all about this ratio of the things that are trying to cause acceleration, the interactions with other objects, versus our object's own property of inertia, the resistance to all attempts to accelerate. I wrote that in terms of acceleration and net force, but we could also express Newton's second law in terms of some derivatives. We could replace acceleration with the rate of change of velocity, dv dt. And so we see that the rate at which our velocity changes depends on the forces, the interactions trying to change the velocity, and the mass that's trying to keep the velocity the same. That inertia, that resistance to a change in velocity. Or we could also express acceleration as the second time derivative of position. And so d squared r dt squared is equal to the net force over the mass. So all three of these forms are useful at different times. Since Newton's second law is a vector equation, that means that we have to, when we use it, generally write down a version of it for the x direction and a version for the y direction, and even a version for the z direction if we have motion in 3D. So in component form, the form we usually use when we're actually utilizing Newton's second law to solve problems looks like this. The x component of the acceleration comes from the sum of the x components of all the forces, and likewise the y acceleration here. And so if we're summing forces, we do it component-wise. We know how to add vectors. If we got multiple force vectors we adding together, we get the total x. The x component of the net force comes from adding up the x components of all the force vectors, and likewise for the y direction. Still more on the vector nature of this equation. Noting that mass is a scalar, and so the reciprocal of mass is a scalar, this equation says that acceleration, which is a vector, equals this scalar times net force, which is a vector. And therefore, acceleration and net force, those two vectors always point in the same direction. This scale factor just rescales their magnitudes and changes their dimensions, but the direction of the two will always be the same. So acceleration and net force always parallel to each other at every instant, as is described in this very famous haiku: at every instant an object accelerates, parallel net force. One more note here. Newton's second law says that the acceleration of an object at one instant in time, the instantaneous acceleration, is determined by the instantaneous net force. And so when some time later the net force changes, the acceleration changes as well. And so they will be proportional to each other at all times, with 1 over mass as the constant of proportionality. Therefore, if you graph the net force on an object versus time and get this function of some time-dependent net force, the acceleration changes along with it. So whatever the force is, the acceleration is the same thing, just scaled by this constant factor here. So these two functions of time will be exactly the same shape, just scaled differently. That 1 over mass factor could sort of take your force function and stretch it or compress it this way, but otherwise there's no change to the shape. So if you know the shape of this function, you know the shape of that function, and vice versa.